Bjorn Borg, John McEnroe, Boris Becker, Pete Sampras, Marcos Bagladis. What's their connection with Petros Komodromos? None whatsoever. Ah. Petros, you are a teacher at the University of Cyprus.
Yes, I'm a lecturer in the Department of Civil Engineering, and I specialize in the study of the effect of earthquakes on structures. With the use of computers, we try to simulate buildings to understand how these react in the case of an earthquake. One of the subjects we study is new methods in dealing with earthquakes, and specifically seismic insulation. This is a new technology that has come up within the last few years and aims at lowering the seismic load on buildings, thus lowering the effect of earthquakes on built-up areas. Specifically, through conventional design, we can minimize the loss of human lives, but we expect that the building may have to be demolished after the earthquake due to extensive damage, or its use will be disrupted for a long time. Or it may be disused completely. With seismic insulation, we try to avoid having to suspend the use of the particular building or to avoid damages. What engineers try to do is to incorporate plasticity to the building. This is a quality that allows the building to sustain damage, but the damage being controlled and absorbed, thus avoiding the collapse, allowing people to get out. It's understood that in this way, both the structural and non-structural materials can be damaged, and this is acceptable in the case of a strong earthquake. However, as technology improves, it becomes less and less acceptable for a hospital or a bridge, for example, to stop functioning. Therefore, new methods must be used which will reduce stress in the building. Seismic insulation offers exactly that. We incorporate anti-seismic footholds, like the one you have in your hand, at the base, and we allow each leg of the building to sit on top of one of these footholds. While the building moves backwards and forwards as one body, all the stress is confined to the foothold. This results in the seismic insulators, which are designed this way to absorb all the distortion. The building's oscillation becomes very small, and thus the damage to the building and equipment is very small. This is one of two types of seismic insulators. It's made of plastic plates alternately attached to plates of steel. The second type works with friction. This is also a small model, of course. Essentially, one end is attached to the foundation and the other to the upper part of the building. In case of an earthquake stronger than what the structure can sustain, this starts to slide, thus preventing any stress loads to be transferred to the upper structure. In our lab, we try to develop computer programs which will allow us to simulate these structures in order to pinpoint existing problems, or to improve the behavior of seismically insulated buildings. One problem we're looking into at this stage is the case where the structure collides with a surrounding wall or a neighboring building. Seismically insulated buildings are flexible to a large degree, which is the reason why we're looking into this. Therefore, it's important to make a point of having ample space between structures in which the building will be able to oscillate. This space, of course, is usually limited and it's possible for the oscillating building to collide with a structure next to it. We also study the effectiveness of seismic installation, even in such collisions. One idea which we're trying to develop is to attach elastic braces at the possible collision points, like, for example, the bumpers we see on piers. And this is done in order to reduce the effect of a collision on the structure and its neighboring structures. What's more destructive in the case of an earthquake is not the strength of it, but the acceleration of the oscillation it brings on the foundation ground of the building in question. It's important then for civil engineers to measure, using special devices we have at our lab, the accelerations produced during an earthquake. These monitors are in constant operation, and whenever an earthquake occurs, they record it. The data collected is used by our software to simulate the response of the building under study in an earthquake of similar proportions. We also have a database with measurements from previous earthquakes, and we can use these to study how a building would react in real earthquakes that happened in the past.